Good morning. Now, let us start our first class on semester 4. The paper for your semester 4 is Optics and Electricity. So, it has got four units. So, in that, I will be teaching you the fourth unit, namely varying currents. Okay. Now, after completing this unit, I will be taking a few portions from unit 1, 2, or 3. So, before that, uh, I'll teach unit 4, which is varying currents. Okay, so let us begin the first class on our chapter varying currents. Now let us see what are transient currents. Transient currents are nothing but currents that exist only for a very short period of time. You might have noticed when the fan is switched on or when it is switched off, it will run for some time. That is due to the presence of transient current. So the same thing is written here. When an electric switch is turned on or off in some circuit, transient current or voltages will occur for a short period even after these switching actions. That is, when the switch of a fan is switched on or when the switch of a fan is switched off, then just for a few seconds after these switching actions, that is on and off, is performed, a very small current, that is transient current, will exist for a very short interval of time. Okay, so what here you have to study one definition. What are transient currents? Transient currents are nothing that but currents that exist only for a short period of time. Then you can write this example also. And the duration, that is how long this transient current exists, will mainly depend upon the values of various parameters in the circuit, like resistance R, inductance L, capacitance C, etc. Usually the duration of transient current is of the order of microsecond or millisecond. Now this is one of the most important derivations, a possible question for your exams, that is discuss about the growth and decay of current in an inductive resistance circuit, that is in an LR circuit. So today we are going to study about the growth and decay of current in an LR circuit. That is, L stands for inductance and R stands for resistance. So after that we will see various other circuits like CR circuit, etc. So here we are going to learn about the growth and decay of current in an LR circuit, that is a circuit containing only inductance L and resistance R. See, you can see a circuit here, that is, there is an inductance L, a resistance R, there is a switch and a battery of EMF E. So we are going to find out first the growth of current and then the decay of current in an LR circuit. When the circuit is closed, the coil, that is inductance, will oppose the growth of current so that it does not reach its final steady value E by R instantly. So when the current is growing, let I be the current in the circuit and di by dt be the rate of growth of current at an instant of time t. Okay, now the potential difference. Potential difference means the voltage across the resistance R given in the circuit is given by VR equal to IR. That is, VR actually denotes the voltage or potential difference developed across resistance R. It is IR, that is the first equation. Similarly, the potential difference across the inductance L in the circuit, so VL, is given by this expression, that is minus L di by dt. That is equation 2. Now the VL, that is the potential across the inductance VL, will oppose the EMF of the battery, that is capital letter E. Then the net or the total potential difference across the resistance will be given by this equation. That is E minus L di by dt. Why this comes? Because this is the potential across the inductance. This opposes the EMF of the battery E. So we have to write it like this. The difference E minus L di by dt will be the net potential difference across the resistance. So that expression E minus L di by dt will be equal to R, or the potential across the resistance R, that is IR, will be equal to the net potential difference across the resistance. Now from here IR is taken to this side. So it will become E minus IR equal to L di by dt. From that you have to find dt. Just rearrange the terms so you get dt. Now in order to find t, what you have to do? You have to integrate. So integral dt will be t. Then the expression after integrating will be minus L by R logarithm to the base C E minus IR plus C. C is a constant of integration. Now you have to find the value of C. For that, what you have to do is you have to apply a condition. That is, at time t equal to 0, what will be the current in the circuit? I, it will be 0. So just substitute those values in this equation in order to get the value of C. That is, put t equal to 0 and I, this one, equal to 0 in this equation. So when you put like that, you will get the value of C as this one, L by R logarithm to the base C E. This is the value of C. Now just substitute back the value C in the above equation. What was that equation? This one. Just substitute the value of C here. So the final expression will be T equal to this one. Okay. So here you have to, this L by R is common here also, here also. So take that outside and then take that L by R to this side. So it will become R by L T. Then minus is here. So just multiply LHS and RHS with the negative sign. So minus will come here. And when you multiply this side with a minus, this term will become positive. So it will be logarithm to the base C E minus IR minus logarithm to the base C. Okay, so this term is of the form log A minus log B. So that is log A by B, right? So it will be, it again reduces to logarithm to the base C E minus IR by E. These are all simple mathematics. Just take a paper and write down the E steps. Then you will easily understand. Okay, nothing more to teach or nothing more to learn. All these are basic mathematics which you already know. So just take a paper and work out. Then everything will become easy. Okay. There is no steps which is confusing. Now, another simple step. What you are going to do next? Here, so you got the expression as minus R by L T equal to logarithm to the base C E minus IR by E. Now just take the exponential. So this will become E raised to minus R by L T C. And this here, this log will go. So it will be E minus IR by E. This is again equal to, that is E minus IR by E will be E minus IR by E. You are dividing each of these terms with the E. So E by E 1 minus IR by E. That is what written here. Okay. Now, so from here IR by E, what will be IR by E? It will be, you are taking this one here. So it will be 1 minus E raised to minus R by L T. And what will be I from this equation? Just take R by E to this side. So it will become E by R. The other thing is kept as such. So again this equation reduces to I equal to E by R is replaced by the term I0. This term is kept as such. So this is the final expression for the growth of current in an LR circuit. See, this diagram is also important. You have to study this diagram. Current is increasing slowly with increase of time in an exponential manner, reaches a maximum value E0. E0 is nothing but E by R. Okay, now this equation is also called by the name Hellman's equation for the growth of current in an LR circuit. That is, it shows that the current rises exponentially, and that is shown in this particular figure. Now from here you have to find out the inductive time constant. The ratio L by R is called inductive time constant. It is denoted by the letter tau L. So we are going to put the T as tau L or L by R. Okay, so what will be the equation here? I equal to, this equation 3 will reduce to I equal to I0 1 minus e raised to minus, here L by R is written as T. So what will be R by L? It will be 1 by T, right? So e raised to minus T by T. It will become like this, e raised to minus T by T. T by T is 1. So e raised to minus 1. That is what written here. Just substitute the value L by R in equation 3. So I will become, it reduces to I equal to I0 1 minus e raised to minus 1. E raised to minus 1 is 1 by e. Now the answer for, just substitute the value of e. E value is 2.718. So 1 divided by 2.718 is, calculate that and subtract 1 from that value. So you will get it as 0.632. So I equal to 0.632 I0. Now the inductive time constant of an LR circuit is defined as a time in which current grows from 0 to 0.632 of its steady value. So study that definition also. So that's all about the equation and graph about the growth of current in an LR circuit. Now in the same circuit we have to discuss about the decay of current. So let us start with a similar equation. The pattern is same, only there is a slight change in the sum of the equations. Okay, let's start. Now when the switch in the circuit diagram, yes, if it is thrown over to B, the current in the circuit decays. That is, let us see the decay of current in the LR circuit which is shown above. In such cases, the EMF in the coil will oppose the decay of current. So this is the equation for decay. So you have to start with this equation for decay. So you have to begin the sentence as this. Consider the decay of current in the LR circuit given above. The equation for decay is given by minus L di by dt to IR. What is minus L di by dt? It is the potential difference developed across the inductance L in the circuit. What is IR? It is a potential difference developed across the resistance R in the circuit. Okay. So the decay equation is, you have to equate those potential across V, potential across L and potential across R. So that is minus L di by dt equal to IR. So from that, just rearrange the equation. From that you have to find dt. On integrating, you get the value of t as minus L by R logarithm to the base C I plus C, similar to what we have discussed earlier. Now what is the next step? As discussed in the growth of current, you have to find the value of C. What is the value of C? For that you have to apply a condition. Here the condition is at time t equal to 0, I equal to I0. But what was the condition that we have applied to find the value of C in case of growth of current? At time t equal to 0, I equal to 0. But here in case of decay, our condition is at time t equal to 0, I equal to I0. So just like that, everything is same, but there will be a small changes in some of the equations and also in some of the conditions that we apply. Okay, otherwise it is very easy to learn. So just apply that equation. At time t equal to 0, I equal to I0. So you will get the value of C as L by R log E I0. Now substitute the value of this particular C in this equation. So you get the equation as, this equation as t equal to minus L by R logarithm to the base C I plus log L by R logarithm to the base C I0. Now just as what we have done, L by R is common. So take it outside and then take it to the other side. So it will become R by L. T is kept as such. Then you are multiplying both LHS and RHS with a negative sign. So a negative sign appears here. When this side is multiplied with negative sign, this will become positive. So it will be logarithm to the base C I minus, this will become negative, logarithm to the base C I0. This is of the form log A minus log B. That is nothing but log A by B. So log e I minus log e I0 will be log e I by I0. Now you are removing the logarithm part, so here you will get, you have to put an e here, the other term will be I by I0. So from that you have to find I equal to I0 equal to minus R by LT. This is nothing but, as said before, this is the Helmholtz equation for decay of current in the LR circuit. Here there is graph shows the exponential decay. Okay, this is the main maximum value I, t, etc. So exponential growth and exponential decay we have seen. Now here also you have to find inductive time constant. Just as said before, put t equal to tau L equal to L by R in equation 5. So this is your equation 5. So this one, how, what will it be? L by R is t. So R by L will be 1 by t. So it will be I equal to I0 e raised to minus t by t. That is I equal to I0 e raised to minus 1. Okay, so e raised to minus 1 is 1 by e. So I is again equal to I0 by e. Value of I is 2.718. So finally it reduces to 0.368 I0. Thus inductive time constant of an LR circuit is defined as time in which current decays from maximum to 0.368 of the maximum value. So this is one of the expected questions. So in today's session you have to study what is decay current, what are varying currents. Okay, and then you have to study both, that is both the decay and the growth of current in an LR circuit. Okay, today this is enough. Thank you. So about one more thing. Anyway, this chapter is about varying currents, right? So along with this video, I will upload full notes on this chapter, varying currents. Okay, so on each week I will take small portions on that, about the notes that is already uploaded. Okay, so along with this video I will upload the full notes on this chapter, varying currents. Okay, okay then, thank you.